Hello. So this is convert sorted array to binary search tree. Given an integer array nums where the elements are in ascended order, convert it to a height balanced binary search tree. So let's look at an example. So we're given an array nums and the output, which looks like an array, but it's just a representation of the binary search tree. We'll have 0, -3 as the left child, 9 as the right child, -10 as the left child of -3, null as the right child of -3, 5 as the left child of 9, and yeah. And so this is a height balanced tree because we can see that the height here is balanced and same as here. A non-balanced tree would look something like this. Let's say we just iterate through nums and we're creating the binary search tree. -3 would be greater than 10. 0 is greater than -3. 5 is greater than 0. And 9 is greater than 5. So this is technically a binary tree, right? But it's not balanced. Hey, so let's dive into this problem. We have a tree node where the root is 0. So it happens that 0 is in the middle of this array. I don't think that's a coincidence. This is a binary search tree. And I know it's a weird connection, but this in a binary search algorithm, you have a left and right pointer. And then you want to calculate the middle and do something with either the left or right side. It just so happens in this case on a binary search tree, since we're creating one, we're going to need to do something on both sides of the array. So once we calculate the middle, we can simply create a tree node for that element. That satisfies the top of the tree node in this example. And essentially, we need to be able to create a binary search tree on the left side and the right side. And we're simply just going to do that same operation on the left side of the array and the right side of the array. So don't overthink it. This is recursive. I hate thinking recursively, but just like a binary search, let's just work on the right, left side first. So we're going to move this pointer over to m-1, which will be here. And we'll essentially want to assign that, and we can talk about this later, how this works. We want to assign that to the left side of this tree node, right? We're not assigning the array, it's just a visual representation. We have a left and a right. And so what we're going to want to do is create, or we're going to want to find the middle. In this case, let's floor it. So the flooring of this middle would be -10. So we're going to simply create the node for -10. Nice. Now there is no left side, but let's just keep going, right? Let's keep going on what the quote unquote left side would be. So the right would move to r or m-1. And as you can see, in a binary search algorithm, once L or R crosses each other, then we're at the end of the base case or algorithm. So in this case, if let's say R and L pass each other, we can simply return, we have to return something, right? So let's return null. So that's typically how it's visualized in a binary search tree. Cool. Now we can actually go back to this array where we had our m, and instead of working on the left side, right, we can work on the right side. So now L needs to be where m plus 1 is, which will be where this right pointer is. So on the right side of this, we're going to say, what is the middle of this array? It's -3, so m's actually here. We're going to put -3 here because, like I said, once we calculate the middle, we're going to create a tree node. Boom. And then we can keep going technically in our logic and put L where m plus 1 is, which will be crossed. And like we said, once it crosses, it'll be null. And we could technically do the same check on this array on the quote unquote left side, and that would be null, right? But we don't have to overthink it. we can come back all the way back to where we calculated this, right? That's where this one is. We also need to do the left side, right? So on the left side, we'll calculate 5 and 9. Again, this is just a representation. We'll have the left node, we'll have the right node, we'll calculate m. In this case, it'll be the floor, and we'll create a node for 5. And then so on and so on, we'll create one for 9. So I hope that made sense. I think the code will help you better understand it. All right, let's start coding. So we have a tree node that they give us, which is the definition for that binary tree node. It gives us the value, the left, which is a reference to the tree node, and a right, which is a reference to the tree node. And we have a nice constructor to call upon this. So being a recursive solution, I think there are 3 ways that you can actually approach it. I'm going to go with my favorite approach first, but I'll also touch on the other 2 that I know of. And my favorite way to approach a recursive problem is to have a inner function or a helper function that people like to call it. It's just easier for me to name right now. So this function will help us with our recursion and will help us start our recursion. I like it this way because it's more intuitive, but it's not de facto. I'll show you the other methods, but let's just stick with this one for now. So in our solution, we need to calculate that middle index, right? Just like any binary search problem. So we're going to need a left pointer and a right pointer. And we're going to want to calculate the middle. And that's usually calculated with this. It's going to be r plus l, and we're dividing that by 2. And once we have our middle, we said we were going to create that tree node, right? And this is essentially the meat of it. Let's just say like nums was just a size of 1, After we call this helper function, we should also return the root. This will technically be right, but obviously we want to make it recursive so it works for all types of scenarios. And so we want to do this exact same logic on the left side of the array now and the right side. So we simply just want to recall this method. But if we just recall this method as is, it will simply just use the same left and right pointers, which will create the same tree node from the same value of m, right? So we need a way to tell it, hey, I want it to work on the left side of the array. And that's typically done with our pointers. So instead of hard coding this in here, we should probably pass it in so it knows where to work with. And this is the first case that we need to use. And the place where we're calling the recursive function first is going to be here. So we can simply just pass these in, right, to work on that first tree node. And then once we call the helper, we need to move our pointers. We want to work on the left side. That typically means leaving the left pointer where it is and moving the right pointer where the middle was, -1. And for the right side, we're going to put the left pointer where middle was, +1, and leave the right as it was. So now we have these 2 lines of code that creates the tree node on the left side, from the left side of the array and the right side of the array. But there's no connection to it. So in order to connect them, we have that reference here and here. So now that they're connected. And don't kill yourself trying to go through the entire example. As long as that first step kind of makes sense, it's recursive, so it should make sense it should make sense for the rest of the inputs. So let's go ahead and run this. We're going to get a maximum call stack size exceeded. So why is that? So just like in a binary search problem, we have that condition to know when to break out of that loop. We need that same condition in a recursive function. So if that left pointer exceeds that right pointer, then we're going to return null in this case. Before we were returning root, but once we're out of that recursive function, we want to return null, which also represents an empty node. Let's submit it actually to see if we pass our test. And nice, not bad. So I just want to quickly go over the other two solutions for a recursive problem. Essentially, instead of having a helper function, we will be using the given function. So we have the same logic, right? We need to find that middle pointer. And with that middle pointer, we need to create a root and then work on the left and right side. So instead of having our left and right pointers, we actually have to manipulate the given input. So instead of left and right pointers, right, we will instead say nums.length divided by 2, right? It's essentially the same thing. And so once we create our root node, which is fine, our left side, we're going to want to recall the function. And instead of passing in pointers, we just pass in the manipulated input, which in this case, the left stays the same, and the right gets moved to the middle. The way slice works is it stops where this ending is, so stop right before, so we don't have to do -1. And then we'll do the same thing on this side, except it will start where middle is +1. And it will end where nums.length is, but in a slice, you don't have to enter that. And then we will simply return the root. So let's run this, see if it works. So we need that base condition again. So if nums.length is empty, then we're going to return. Do a little format, run it. Boom. And then the third method, it's very similar to this one. It doesn't really work in Leetcode, but instead of manipulating that input array, you could pass it extra parameters, in this case, that left and right pointer, and use those. So really, if we go back to the original solution, right? Instead of having helper here, we're passing in the pointers to the original array. Boom, boom, boom. And then we pass in the unmanipulated input array. And we can't run this because, Leetcode is expecting a function with one parameter, but yeah, that is also another method. Hope this helped. Thank you.